Love me and leave me in luxuries now. Hot when I holler, skip when I snap, when I say do it. Send out a star.
Okay, let's see. Sarah B. Yep. Claire. Matt. Luke. Jaden. Emma. No, where is Emma? Not here. Sorry, I spaced. Liza. Yeah. Stuart. Ethan. Manya. Olivia. Kashal. Diego. Darwin. Sean. Jules. Doa. Matthew. Colin. Rennick. There he is. Perfect timing. Sarah T. McKenna. Okay, several of y'all just came in. Oh, there's Emma. Okay. Olivia. Thank you. Anybody else come in whose name I didn't call yet? Do I have everybody? Okay. All right. Okay, so time to get started. We were talking about spherical coordinates before the break. By the way, I hope everybody had a good break. Welcome back. But yeah, we were talking about spherical coordinates, and we were almost done, frankly. And I just want to do this one last example before we move on to the next thing. Mostly because this is an art challenge, this particular question. So we're looking for the collection of points that are inside of this ball, right? But outside of this ball. So not allowed to be in this ball here, right? And so all together then what we're interested in, I mean, the actual set we're interested in, I'm going to make a poor drawing of it here by doing that, right? And having done that, let me criticize my own drawing here now. What's wrong with this drawing is it makes it look like that there's sort of nothing here, but that's not really quite true, is it? Because really the bottom sphere has taken a spherical hole out of the bottom of the top ball, not a conical or not a cylindrical one, right? So there's actually kind of a lip that goes around like that. around the bottom. And so you can see it's just not, it's going to be hard to make a good drawing of this. And then hard to visualize, you know, once you've got a drawing, it's not going to be a good one. Trying to visualize, okay, well, what do slices of it look like? Right now, it's not that you can't figure that out, and it's not you can't think that through, but there's an easier way. What I do think is clear is that this solid, when it's all said and done, it goes all the way around the z-axis. So the theta range is pretty clear. Yeah.
I feel like this might be a silly question, but
It's okay.
what in the like definition or like the given equation
Yeah.
tells you that it's not in the second ball?
Oh, yeah,
Like,
because,
what
yeah, so
communication?
so distance from the origin, well, distance squared from the origin has to be greater than 1. And that's a way of saying it has to be outside of this ball here, because there's the origin.
Okay.
And if distance, yeah,
Okay.
is that cool?
Yeah, thank you.
No problem. Okay, so yeah, so the theta part is pretty straightforward. So really, all we really need to understand about this solid is not what it looks like, but what its theta cross sections look like, so that we can get down to the harder question of figuring out the range of values of phi and the range of values of rho, stuff like that. So if all I really need to draw is a slice, I need to draw a theta slice then of it. The clever observation to make is that I don't actually have to visualize the solid to slice it, because this solid is made up out of balls, as it were, and slices of balls are easy. Slices of balls are discs, all right? So what I'm going to do is point out that, okay, well, this slice of this ball is clearly a half disc, right? And a slice of this ball is, well, it's a different half disc. And I'm looking for what's inside the green, but outside of the blue. Okay, no problem. Inside of the green, outside of the blue, there it is. It's that. Or again, as y'all recall, I like to draw these things, you know, draw the theta cross sections over so you can look straight on at it. And there it is. It's really easy to see a picture of after all, right? So I do think this is a useful little trick. And that is, again, don't necessarily feel like you have to visualize the entire solid. If you know what you need to know about the theta range is sufficiently clear, you don't actually have to draw the solid, you only have to draw the slice. And it's easy to draw slices if you think about how the easier objects that make up your solid might be easier to draw slices of. Okay. All righty, so that's all I wanted to. So by the way, of course, more details here. And this is very much like examples we've already done. So for example, trying to understand this point, that's going to be our largest phi value, right? Very convenient that we can see that this is an equilateral triangle, and that tells us that angle is pi over 3. So we've talked about things like that before, but there you go. Yes.
How do you know that the third side is?
Yeah, sure. Okay, so this and this are radii of that circle,
Oh, okay.
right? Oh, and then this one is a radius of that circle. Yeah. Okie dokie. Okay, so moving along. By the way, we're still in section 5.5. It's massive section. It really should have been 2 sections. Frankly, again, it would have been 2 large sections. But it's this monster as it stands. So the last thing I want to talk about is an important, I think a very important computational tool that is that I've seen not really discussed in the book at all. And I think that's a huge omission. But the symmetry theorems for double and triple integrals are really actually fairly easy to talk about, and they're extremely powerful and extremely useful in practice. So I want to start by reminding y'all of an old single variable calculus result. I'm sure y'all seen this before, but this neat fact here: if you have a function, if your integrand is odd, and if your domain is symmetric, then the integral is 0. I hope everybody's seen this before. It's by the way, if you have not, then FYI, what an odd function is. It's a function that has this feature. Odd powers of x have this feature. Thus the name. And then a symmetric interval is just an interval that, roughly speaking, it's like from negative k to k. Right? It's symmetric around the origin in some sense. Okay. All right. Now, why is this theorem true? There's a sort of a Riemann sum point of view on this. This is kind of the most intuitively satisfying way to convince yourself that this theorem is true. If you think about the actual Riemann sum that you add up when you're looking at, on the interval from negative a to a, and you're looking at all these different slices, adding up a whole bunch of different slices there, right? Then they pair up and cancel in a very convenient way. So in particular, if you look at this term, that's one of these terms in there. And then you look at this term, also, there we go, also one of the terms in there. Well, by oddness, these are negatives of each other, because f of p and f of negative p are by definition of what it means for a function to be odd. Those are negatives of each other. And because they're negative, those two terms cancel. Right? And then furthermore, how do I know that every term is going to pair up, like with one of the other terms? How do I know there's going to always be pairing? Well, that's because of the symmetry, right? So because this interval goes from negative a to a, and it's symmetric, every term over here, well, there will be a corresponding term over there. So everybody pairs up, everybody cancels, nothing's left, integral 0. Okay, now that said, I do want to show you a way to prove this a little bit more algebraically, and that's to use a substitution. So real easy substitution, as it turns out. So here's the integral that I want to prove is equal to 0, and by the symmetry of the domain, the interval and its reflection. Now keep in mind what g does. G just multiplies by -1 there. This interval is its own reflection, right? And then now later in the calculation, we're going to notice that we'll have a moment where f of negative something comes up. And of course, that's the negative of f of that something in there is where the oddness kicks in. So we have a symmetry of the domain. We have the oddness of the function. That's kind of the easy beginning and the easy ending. The meat of the argument, though, is what happens in the middle. If you look here now at this step, I claim that this integral here is equal to this integral here, and specifically it's a substitution. It's a pullback. Notice we start here with an integral over an image. That's what substitutions are. It's change of variables, right? It's dealing with an integral done over an image. And if you have an integral over an image, you can pull back to the pre-image. In the integrand, you just kind of plug in your substitution formula, or your change of variables function, whatever you want to call it. And then don't forget your stretching factor. I claim here the stretching factor is 1. Stretching factor is 1 because, I could write this down algebraically, but I'm going to just make an intuitive argument. The reflection, it just does this. Right? Nothing's getting bigger or smaller in a reflection. I'm just going to make that as an intuitive appeal. You should not make such intuitive appeals on an exam, but just to save us a lot of trouble, I'm going to make it intuitive here. But there's the stretching factor, and so we're kind of done then. This integral by symmetry is equal to that integral, which by a pullback is equal to that integral, which then by oddness is equal to this, and that means that this integral is its own negative And if an integral is its own negative, if any number is its own negative, well, then it's 0. So, everybody see the argument? All right, so why did we just spend a bunch of time talking about single variable calculus? Again, hopefully this is a review, or at least in some sense for y'all. The reason we just talked about the single variable is because there is a multivariable version of this. And as I show you the multivariable version, I want you to think about how it's just the same idea, total ripoffs of the ideas that we just talked about, just in a multivariable setting. So we're going to define a two-dimensional analog of this move right here, where you take a value and then you look at its negative, right? So the analog there of multiplying by -1, you can think of this as kind of reflecting over the origin. Well, in 2 dimensions, we need to reflect over a line. And now you'll notice I've drawn this line at kind of an angle. Most of the time you won't be reflecting over lines at weird angles like this. Most of the time you'll be reflecting over the y-axis or the x-axis, or maybe a line on the 45-degree or something like that, right? But I'm drawing it at an angle here just to emphasize it could be any line. So pick your favorite line in some sense. Yes?
So it has to be straight.
It does have to be a straight line. Yeah. That's right. Okay, so this picture defines what I call the reflection function, right? And we're going to use that to make a theorem. So with this, oh, by the way, what the formula for this function depends on the line. And one of the annoyances of using a symmetry argument is that you're going to have to look at each line that you plan to make a symmetry argument with separately and look at the geometry of the situation and identify what the formula for the reflection is for that line. It's always every line, different reflection formula. We'll get to those details in a second. So I'm going to define oddness and symmetry of a domain in analogous ways. Oddness means a minus sign when you reflect. That's, again, I think this is highly analogous to what we did in the single variable case. A domain is symmetric if anytime you have a point in the domain, it's reflection also in the domain. Now, this is a different way of saying symmetry, but I think that's pretty plausible, right? If as you reflect everything over on this side that's in the set, its reflection over here. This is kind of a mathematical way of describing, a Rorschach image, So again, analogous to what we did in single variable. And with these things defined, I'm going to claim, and we'll prove in just a second, but I'm going to claim that the exact same theorem holds. Okay. All right. So in particular, if your integrand is odd, if your domain is symmetric, then the integral is 0. Okay, I don't know what that sound is. Sorry, that's very distracting. Okay, all righty. So do be careful of one thing, though. It is very important both conditions have to hold. One of the classic blunders that students will make is they'll see a symmetric domain and just think, oh, hey, the domain's symmetric. Boom, integral 0. Not so. You have to have both of these conditions. The function also must be odd. The other classic blunder that students will make is to forget that it does have to be over the same line for the argument to work, and you'll see why in just a second. Again, as I go through the proof. But super heads up on those 2 points. If you step on either one of these landmines, then your argument doesn't work, doesn't make sense. Okay. All righty. So first of all, let me show you how to prove this with the the algebraic proof. And it's really, again, highly analogous to the argument we made in the single variable case using a substitution. Here, instead of a substitution, it's a change of variables, but it's morally the same. So first, I notice that because of the symmetry, the domain is its own reflection. That's what it means for a set to be symmetric. And then I further recall that the value of a function f, an odd function f, at the reflection point is the negative of the original value of the function. That's the definition of oddness. So again, it all comes down to this one step right here. Everything else just kind of falls into place. How do I know that I can take this step? Well, notice I have an integral over an image. When we have an integral over an image, we do a change of variables, right? You pull back the domain. You plug in for the change of variables function. So the output point is the reflection of the input point. That's just plugging in the change of variables. Don't forget your stretching factor. Again, we're talking about a reflection. So this is what our reflection looks like, right? How much do things get stretched by doing this? Well, not at all. And again, I want to make this an intuitive argument. Because I want my result to still work if I reflect over an angled line or some line I haven't anticipated, right? Computing a general Jacobian for a general reflection is just a little, I don't want to. It's tedium that I think is, again, intuitively satisfying anyway. So I'm just going to assert that reflections don't have stretching factors. Yeah, so this integral is its own negative and therefore 0. Okay. All right. So by the way, in case you were wondering why all of this discussion started happening in the section on change of variables, this is why. It's because change of variables is at the heart of the argument that allows us to know that these theorems that we're writing down are actually true. Okay. How's everybody doing? Is everybody with me so far? We got an example coming up. Yes.
I'm just a little confused about how the change of variable gets us from what you have above to the double integral of d.
You're wondering this step right here?
Yeah.
Yeah.
So like, I mean,
You know what might make it easier, honestly, is I arguably should have used a different variable down here. So I arguably could have had this be, the u vector, something like that. So in other words, x being r of u. So this is effectively my change of variables function. And when you do a change of variables, what you do in terms of the integrand is you just try to plug in, and this x here, according to that, x is r of u. Is that what you were wondering about?
But does r of d represent the limit of integration?
Yeah, well, that's right. So r of d is the domain, so I keep in mind my actual domain is d, but I want to capitalize on the fact that I have a symmetric domain, and symmetric domains are their own reflections, right? I mean, it's like a Rorschach diagram, right? It is its own reflection. That's its symmetry is the fact that it is its own reflection. And why would I want to complicate matters further by viewing this in the more complicated way as being its own reflection? It's because that's what allows me to then do the pullback.
But did I say the odd functions, like x cubed, it's positive on one side, and then if we were to go to the negative side, the reflection side of the integral would be a different side.
Yep, that's what happened here.
Why did that happen on the first line when you went from D to R?
Because I'm not reflecting. So all of this is the same. I'm not reflecting the point here. I'm just making this first line is actually a very innocent observation. These are the same sets. In this first line here, I'm not doing a change of variables. I'm just saying, hey, D and R of D are literally the same set. So in some sense, nothing happens on the first line. Is that cool? Yeah, I'm just on the first line here. I'm just saying that this domain that I have, well, in fact, it is an image. Weirdly, yeah. Is that cool? Yeah. Okay, so now there's a different point of view you can take on the symmetry, and this is again kind of the Riemann sum point of view. And so if we have some domain here, I tried to. It's hard to draw a symmetric domain, by the way, so that's why I went a little bit geometric with this. But if it's symmetric over a line, then every sort of little piece of area you might be interested in, well, there is a reflection of that piece of area. And for each one of these, I can talk about the corresponding term in the Riemann sum. And let's see here. Yeah. Corresponding term in the Riemann sum. By the oddness feature, I know that these are negatives of each other. And so they cancel in the summation. So this argument here is really just a two-dimensional version of this argument. Yeah.
So you said you didn't want to do like, the algebra to show that the stretching factor is 1, but you said that wouldn't be sufficient like on an exam.
Yeah, well, this on an exam, I wouldn't ask you to prove this.
Okay. So
Yeah.
just, like, kind of
On an
like-
exam, I'd give you something very specific,
Okay,
right?
gotcha.
I just, in order to generalize, what is the formula for this reflection, reflection over an arbitrary line. I mean, I can do it, but we don't want to get bogged down in
Okay.
that. Yeah, that's all it is. Yeah.
Thank you.
No, I'm not going to ask y'all to do something that I'm scared of. Right. Okay. All right. So let's get our hands dirty and actually do one. Here is my first example I want to show you. Suppose I have my domain for an integral is bounded by these two curves, and we can draw a picture of these curves. I'll draw a very quick picture of these two curves. So x squared minus x to the fourth is, it's something like, oh gosh, like this. And then y equals -1 is, of course, about like that. So my domain is what's bounded by those. My domain is this thing in here. And I'm going to make an intuitive appeal here as well. That's symmetric. I mean, it looks symmetric, doesn't it? Now, if you want to get careful, right, and precise, how do I know that this is symmetric? Here is an argument. I'll point out that if you plug in a reflection into either one of these curves, let's take this curve right here. If you plug in the reflection, well, first of all, we have to think about what the reflection is. The reflection over that line is this formula. Right, when you reflect over the y-axis, x gets a minus sign and y doesn't change. And when you plug in this reflection into that equation, you get the same equation. So the reflection of that blue curve is itself, and so it's a symmetric curve. And then, same for the purple curve. Of course, nothing happens with the purple curve. So anyway, yes, you can do that, but it's also sometimes just pretty intuitively satisfying that, once you see what the domain looks like, that okay, it's pretty clearly symmetric, and that's fine. Okay. So I claim further that our integrand, this business here, I claim that is odd, has odd symmetry over the y-axis. Now, this does require some algebra. That's a kind of a nasty looking function there that I'm claiming is odd. So here we really do need to plug in and do some algebra. And in particular, of course, I'm going to take my reflection, plug in what my reflection is. Now, the tricky part of where a lot of students do get confused is the process of plugging in the reflection into the function. So keep in mind, when I say f of negative x comma y, what that means is that negative x goes in to where all of these x's are. Is that cool? It's easy to get that messed up. If you're worried about the possibility that you might mess that up, here's a nice little hack workaround. You can rewrite your integrand in terms of other variables. Just pick different dummy variables. Maybe, for example, you might write f of s comma t is, well, it's s cubed e to the s squared plus 1 minus now t sine of s. And then here, there's really no confusion. I mean, so in other words, when you say f of negative x comma y here, well, negative x is s. Boom, boom, boom. And it's just perfectly clear, no confusion. A way to say, is it x or is it negative x, right? That's unambiguous. So again, if you want to leave less to your sort of imagination, then feel free to rewrite the function you're trying to prove is odd in terms of different dummy variables, and takes away some of the potential confusion. But you don't have to do that if you don't want to. And then we just have to do some algebra. Negative x cubed, of course, is the negative of x cubed. Negative x squared, though, is exactly x squared. Negative sine of negative x, well, don't forget sine is an odd function, and so sine of negative x is the negative of the sine of x, and so we have a negative of a negative, which is just positive sine x. Everybody good? And sure enough, this is the exact negative of the original function. So sure enough, as desired, this function is odd. And we are done, right? So we had this nasty integral. It almost kind of feels like we've been kind of working side questions and not really addressing the actual business at hand of how do I compute this integral. But we are done. This integral is 0. No antiderivatives necessary. No slicing and dicing necessary. Don't have to worry about bounds and such. Domain is symmetric. Function is odd. Same line. Poof. Everybody happy? Okay. All right. So super powerful method. Unthinkably difficult integral, kind of, right? Yowzers, right? How are you gonna, oh my God, what a nightmare. Boom, 0. So this is why I am such a big fan of the symmetry theorems, and why I'm disappointed that I don't see them. Maybe I just missed it, but I haven't seen them yet in the textbook. They turn monster problems into trivialities. Sometimes. So I have a lot of past experience myself with this. So again, I'll remind you all, my second major in college was physics, and I think it was 9 physics classes I had to take for the physics major. And my, back of the envelope, based on distant memories estimate of those 9 physics classes is, I think, about 20% of the integrals that I computed. And there were a lot in a physics major, right? About 20% of the integrals that I encountered were 0 by symmetry. That's a lot of integrals, right? Now, a lot of y'all are engineers. Engineering's not that different from physics. There's a lot of integrals in your future, right? So this is arguably one of the most important theorems in how to integrate stuff that you'll see. Okay. Is that cool? All right. Now I have a related point I want to make, and that is that the tons and tons of integrals that I encountered on homework exercises and that kind of thing. Yes, but also on exams. And very convenient to know on an exam that you can make a symmetry argument, and boom, the whole integral just turns into 0. So I did that in college, but I also did it on a handful of occasions when I actually didn't make the complete argument, and I didn't have time to make the complete argument. How we all know, sometimes you're taking an exam, you're working as fast as you can, and you look up and you realize you have 45 seconds left. And there's a whole question here, which is compute the following integral, right? Or something along those lines. So what are you going to do? And so I came up with the strategy. I'm sure I'm not the first of just, in such a situation, I have no chance of actually being able to crank out the details myself of just writing integral equals 0 by symmetry and just turn the paper in. Fingers crossed, hope that works. Right? And it worked for me at least once. Right? And I got full credit on a whim, right? It was a total Hail Mary pass. I don't know, maybe someone will catch it, and I should not have gotten those points, right? That I didn't deserve that. So I, with that in mind, have certain rules. If you're going to use a symmetry argument, I'm hep to the con, right? You do have to actually make the argument, and specifically, there are 5 elements that I require to consider a symmetry argument a complete argument. So for one thing, the line of symmetry is, right? There's lots of different lines. There may be lots of different candidates that you could, maybe they work, maybe they don't for the integral at hand. So you got to tell me, which one are you picking, right? What is your line of symmetry? I need to see the formula for the reflection. Because that is going to be essential in the item number 4 coming below. You have to note that the function is odd, and I say correct here in parentheses because you can't just assert it's odd if it isn't, right? It does have to actually be odd. So you have to correctly observe the function's odd, and then furthermore, you have to prove it, right? This algebra up here, I got to see that algebra. It's usually not immediately obvious, right? There is some algebraic work to be done. And then, of course, you have to have a symmetric domain. So you have to state for the record that you are using the fact that the domain is symmetric. Now here, do you have to demonstrate that the domain is symmetric? No, again, that's geometrically usually pretty clear. If it is, if the domain actually is symmetric, it's usually also clear that it's symmetric. And so that I think it's a reasonable to just kind of, I don't require any such demonstration. You do have to be correct. Again, I emphasize, if you claim something symmetric when it isn't, then not only is your argument invalid, but I guess that's really the point though, that your argument's invalid. But symmetry argument does not work. There is no symmetry argument to be made if your domain is not symmetric. So do be careful about that. Yeah, I saw hands. Well, yeah.
Yeah, so for that example,
Yeah.
just saying, like the y-axis.
Yep.
Write out like L equals.
No, you can just say the y-axis. You just have to identify it. That's fine. You got to the reflection. Let's see here. I observed correctly that F is odd. And yeah, etc. Is that cool? Okay, yes.
So the way to know the domain is symmetric is from looking at the picture?
Yeah. Draw a picture, unless it's clear. Like if the domain is the unit disk and you're claiming that it's symmetric over the x-axis, yeah, it's clear. No picture necessary. Yeah, but if it's something non-trivial like this, then yeah, you'd want to draw a picture. Yeah. Okay. All right, now, notice there's a lot of components that go into a complete symmetry argument. All right, you got all these different things that have to go into it. They all have to apply. right? It's not just that I'm saying that you have to say them. I'm saying they all have to actually apply. If you have a line of symmetry and a valid formula for the reflection, and you've correctly observed the function is odd, you've proved that the function of odd is odd. But if the domain simply isn't symmetric, there is no symmetry argument. You did not make 80% of a valid symmetry argument. You made 80% of an invalid symmetry argument. You're 80% of the way towards nothing, right? So this is a big bummer downside of making a symmetry argument, is that if you're mistaken, nothing on the page is actually relevant toward an actual solution. Right. And so again, it's very, very dangerous. So do be careful if you're going to make a symmetry argument. Think it through slowly and carefully. Go ahead and take those extra few seconds. Am I sure this thing is symmetric? Am I sure that the function is odd? Am I seeing the reflection correctly here? Just be sure that you're right. Because again, otherwise it's nothing. All right, so here's the next example, an integral to be computed, not that it's a hard one. This wouldn't be bad. And so what if a student wrote, hey, the domain's symmetric, the function has odd symmetry, boom, integrals equals 0 by symmetry, walk away. And here's the thing. I mean, what's said here, these are all true facts. This domain is symmetric. That's true. This function does have odd symmetry. Yeah. The result is true. This integral is equal to 0 by symmetry, but this is not a complete symmetry argument. And in fact, you'll notice that while domain is symmetric, yep, got those points. This has odd symmetry, yep, got those points as well. But nowhere in what is written here is it stated what is the line of symmetry that you're using, right? What is the formula for the reflection? Where is the demonstration that this function is odd? Are you sure this function's odd? Right? So this student would get somewhere in the ballpark of having done 2/5 of the 5 required items. I mean, I wouldn't say that they're always worth the same number of points, but this student's getting somewhere in the range of 4 out of 10 points. In fact, maybe a little less than 4, because the one that requires the most work most of the time is the one that demonstrating that the function is odd, and that was one of the missing ones. So anyway, so again, I love symmetry arguments, near and dear to my heart, big fan. You gotta give me all 5 of the necessary elements. Yes.
Would you be able to show us how to do the ones that you did before?
Well, I'm on a schedule. I do have other examples coming. Yeah. But I do want to get as much time. We're 2 days behind schedule here at this point. We kind of have to make it. But come to office hours. I'll be very happy to give you all the details on this in office hours. Yeah. Okay. So here's another example. This one's harder. Weird shaped domain. Highly undesirable domain, right? Corners everywhere, weird curves. Not that I couldn't do it, but this is going to be a massive pain to do this the old-fashioned way. Spherical coordinates doesn't help, right? I mean, polar coordinates doesn't help. So this is going to, it's a pain to do this directly. But then I notice, look, having drawn a picture of this domain, I can't help but notice it's symmetric over that line. The line x plus y equals 0. It just leaps off the page at me, right? And then I strategize. And I say, all right, well, is it possible that whoever devised this question wants me to break it up into 3 separate pieces and deal with 3 completely separate integrals, some of which are annoying? I mean, I guess it's possible, right? But there's a symmetric domain here what does it, I mean, strategically speaking, doesn't it seem plausible? Hey, maybe there's a symmetry argument. Maybe that's what I'm supposed to do here. Maybe that's why this is a question on this exam or on this homework assignment. Perhaps. Doesn't prove anything. But you should, your eyebrow should be raised. I think this is probably let's investigate the possibility of a symmetry argument here. So that being said, here's the formula for reflection. Now, how do I know that this is the formula for the reflection over this line? This is the kind of thing that you'll, once you've seen it, you'll kind of remember this trick for next time. But if you have a point x comma y, notice that there's the x and this is a 45-degree line. And so I argue that the reflection of that little frame, if you will, is this frame like that. And you can just see that, okay, well, that x is okay. Well, that makes this negative x, and it makes this negative y. And just looking at the picture, and you can persuade yourself without too much trouble that the reflection is this formula right here. What do you think? Yes.
Can you draw those points on the graph?
Draw the what now?
Like the x and the reflection on the original.
Oh, on the original picture? Yeah, so it'd be something like, I mean, it could have been any points over here, but like maybe this point here and its reflection is like right there.
Okay.
Yeah. So every point is going to have a reflection, but that point reflects to that point, etc. Is that cool? Yeah. Okay, so we've got a line of symmetry for the domain. Don't yet know for sure about the function. This business right here. Well, here, let me circle better. This business right here. I wrote this in here in the notes in case you were curious. How would one argue that this domain is symmetric? This is not necessary. You don't have to make the case. You have to assert that the domain is symmetric, and you have to be correct, right? But you don't have to justify why the domain is symmetric. Okay. So now let's check and see if this function is, I guess I have to do like this. Check and see if this function has odd symmetry. Here is our function. And I'm going to take the reflection here, plug it into there. And again, if you want to rewrite in terms of a different pair of dummy variables to avoid confusion of variables, feel free. I find myself typically pretty satisfied by saying, okay, what goes in for the x, right, is this negative y, and then what goes in for the y is this negative x. And so f of the reflection is that. So take your pick, whatever makes you feel better. Again, a little bit of algebra to be done here, but sure enough, you get a minus sign here, and so f of the reflection is the negative of the original f of the original point, and so this function has odd symmetry, and we spike the football. This integral is 0 by symmetry. No fuss, no fuss. Yeah. Okay. All righty. Here's a dangerous one. I already kind of warned you all about this, and I deliberately put this example after the warning because I want to make sure that, I want this to kind of be a little bit of a surprise. But you look at a triangle with those corners. Pretty clear before you even draw the picture. Oh, I see a lot of zeros. There's a 1 and a -1. Not hard to see that there is a symmetry of this triangle. You can draw the picture if you like. Let's look at the integrand. The integrand has an odd exponent, clearly odd. Symmetric domain, odd integrand. Integral 0 by symmetry. You might want to argue. There is no valid symmetry argument for this integral. And the reason why is because the lines of symmetry that give you the symmetries that we just observed are different lines, right? But this domain is only symmetric over the y-axis. Our integrand function is only odd over the x-axis. There is no line that would serve as a symmetry argument for both. So heads up, right? I mean, this is a dangerous little story here. Yeah, if on this question, if you write integral of 0 by symmetry, even if you do some of the 5 steps, even if you prove that the function has an odd symmetry, even if you correctly observe that the integrand is symmetric, it's worth nothing because it's not part of you've not made progress toward any sort of a valid argument because there is no symmetry argument to be made. So this right here, it's tragic to see this, but this does happen sometimes. This is worth 0 points. And it always breaks my heart a little bit when I see that. So please don't do this to me, right? Please don't make me sad for you like this. Does everybody understand the point? Yes.
So for it to be odd over the y-axis, we need to plug in x equals negative x.
Yeah, that's what you got to write the formula for the reflection. And yeah, that's right. Symmetry over the, let's see, where I just had one here. Oh yeah. When you're reflecting over the y-axis, that's right. The reflection is replace x with negative x. Yeah. Okay, so symmetry is very, very powerful, very, very dangerous, and do be careful. Real quick, I'm going to point out you can do the same thing in 3 dimensions. It's just that in 3 dimensions, you reflect over a plane instead of a line, right? But everything else follows through kind of the same. We have the same idea of what oddness means. We have the same idea morally of what it means for a domain to be symmetric. We have the exact same result, the exact same theorem. If your integrand is odd, if your domain is symmetric, if these are both through the same plane, right, and both holding, your integral is 0. So for example, here's a nightmare of a question. If your domain is the unit ball, compute this integral. Let's take a moment to recognize what a nightmare this integral would be by any sort of direct argument. It's a unit ball, so in rectangular coordinates, there's just square roots all over the place in the bounds. So this is horrific in rectangular coordinates. But now, okay, it's the unit ball, which is great in spherical coordinates. So you could totally do this in spherical coordinates. That's, I think, the only reasonable direct approach. But if you do, then X, Y, and Z are chock full of trig. And now you're going to end up with integrals that have trig everywhere, and you're just going to do a nightmare trig integrals just over and over and over again. Not that you can't do it, but so much easier to speculate as follows. And by the way, let's break this down strategically here. There is a symmetry argument. Here it is, fine. But how do I know what plane to pick? The unit ball is symmetric over lots of planes. So which one do I choose, right? And sometimes the domain will be the giveaway. Sometimes the domain is the tip. Like, so, look at this question here. The domain is what suggested to us what the line of symmetry probably ought to be. Yes.
So for something like the unit ball, could you pick, also you could pick the YZ plane?
Well, you can try, but you're going to have a problem. It's going to fail. And so yeah, let me finish. I think I'll answer your question by the process here. So sometimes it's the domain that suggests the line of symmetry. In this case, it's the integrand. So just kind of thinking through, look, if I replace x with negative x, that's not going to give me odd symmetry because that negative sign is just going to get squared and there's no minus sign left over for the oddness, right? But I see that Z is to an odd power. And so roughly speaking, I'm going to reverse engineer and say, in order so that this could be odd, that motivates that I would like my reflection formula to be this. I want to have this minus sign right there in my reflection formula so that the oddness will work out. And then I ask myself, okay, is this actually a reflection, or is this just some weird formula I made up for wishful thinking? And then I have to think through, and yeah, in fact it is, and I can reverse engineer that. That is reflection over this plane. Right, so sometimes you can use the integrand to motivate what a good choice of a symmetry line or symmetry plane might be. In this case, the XY plane. Okay, and having made that choice, well, again, you got to go through the process. There's my plane of symmetry. There's my reflection. The ball is clearly symmetric through that. The function's odd, I claim, because of, well, and there's the argument. And then integral 0 by symmetry. No massive square roots, no massive trig. Easy argument. Oh, I'm sorry, I went 2 minutes over. My apologies. So, okay, we are done with whatever page that is. 40, I think it is. Yeah, done with page 40. Okay, see y'all later. Have a good Monday, and welcome back from spring break.